Hello everyone, it's Prodai. I am currently working on a schedule for posting videos more regularly because, as I believe you know, I don't post them very regularly at all. That's mainly because I don't have that many viewers, but gaining a few, some of my friends and family have decided to learn a bit of computing. I kind of figured that it might be helpful if they know when the videos are coming out so they can know what they're going to learn and maybe what time it will come out. So it's not solid at the moment. I'm still sort of working on it, but it should be out, the schedule, by the time my next video is out. So I hope you enjoyed this video and that by the time of next video you have a bit of an idea of when you can learn this kind of thing. So in the 1930s, George Boole created Boolean logic. His work really started building up from then, and he had the idea of a true or false statement, like I just said, a Boolean statement. And for computing and programming, this is actually quite helpful. You can state some things to a computer. The mathematician actually died from pneumonia after delivering a lecture in wet clothes. He had to travel to the lecture. I think he was in London perhaps, but it was raining. Not a surprise, but yeah, he died. He didn't die delivering the lecture. I did say afterwards, but no, yeah, that wouldn't look too good if he just dropped dead at the front of the stage. Anyways, before George Boole put his ideas into circuits, before he actually made a computer using Boolean, it was kind of just an idea that he had where a computer could make decisions. It could say, okay, there's no point doing this if this doesn't happen. Like I said last time, if you go to the park and start greeting your friends, you want to make sure your friends are there before you say hi to them. Otherwise it looks strange. So he had the idea that a computer could make decisions like this. It could decide it's only going to do the work it's got if it's been given something to do it with. If it's been given no number, there's no point carrying out a sequence because you're not doing anything. So that was his idea. So the first example I'm going to go over is if we want to compare two numbers. If we say, okay, if this number is equal to this number, do this. So the condition is that the two numbers are equal. So we're going to save one of these numbers in ROM, and we're going to use a circuit so that the number in ROM, in the program memory, we're going to test if it's equal to some number that the user puts in, and then the computer might branch or do something based on the condition. So here's the circuit then. If the result is like if the user inputs a 001 001 and we want to test if it's equal to 001 011, then we need to check that wherever there is a 0 on one of the numbers, there has to be a 0 on the other number. So if we want to check if these two numbers are equal, just look at the numbers for a second. 001 011. We need to check that all of the digits are the same. So if we look in the ones column, whatever there is in one of them has to be the same in the other, because if it's different, there are different numbers. So we want to test if they're the same. And also, so as well as there being, if there's a 0 in one of the columns, there's got to be a 0 in the corresponding column of the other number. We have to check if there's a 1 in one of the columns, then there must also be a 1 in the corresponding column. Because if there's a 1 in one column and a 0 in the same column on another number, then that's going to create a different number, because you're literally making different numbers, and when you compare them, they're not the same. So the zeros must line up and the ones must line up. Also, if there is I've said that already, sorry. The way that you compare these numbers is like this diagram I've got below, where you have a relay of XOR gates and you have two inputs. You have the A input and the B input. Now the diagram might be a bit confusing, it's a little modelled up, but here's the idea. If you just have one of these XOR gates, look at XOR gate 1. You have two lines coming from the bottom and one off from the top. You have a and B at the end of the two lines. If A is 1 and B is 0, then the XOR gate is going to give an output. because it will give an output because the inputs are different. That's the definition of an XOR gate. If the inputs are different, it will give an output. So A and B are different. If they are different, then you will get an output. However, if A is equal to 1 and B is also equal to 1, so the corresponding bit is equal, then the output of the XOR gate would just be 0. And what you can do is you can compare every single bit. So if the first bit goes into the first XOR gate, the second bit goes into the second XOR gate, the third bit goes into the third XOR gate, or as I've labelled it here, the bit which demonstrates the number 4, shows the number 4, will go into the XOR gate for that bit. And you have all the A bit inputs going in and all the B inputs going in. And what the XOR gate does is it compares every single bit. But the good thing about connecting all the outputs, as I've done here, is that, well, there you go. You've connected all the outputs. That means that every single bit, if one of them, if the B and A in the first digit, look at the first digit, if the B and A are different, then it will give an output. And that makes all the outputs go on. This means that the numbers aren't equal. And this works for any of the bits. If any of the XOR gates receives two inputs which are different from one another, it will give an output. And that means that even if all the others are the same, that those inputs aren't the same. Those inputs are different, which means that the numbers are different. So they're not the same, so it will give an output. And the output means that the inputs are not equal. If there's no output, it means that wherever there's a 1 in the corresponding bit. Wherever there's a 0, there's a 0 in the corresponding bit. And that won't give an output for anything. So if you have no output, it means the numbers are equal. And that's how the circuit works for a comparator. As it turns out, I had the explanation for the last slide on this slide, which is really annoying. I had to just make up on the spot an explanation because I thought I hadn't put it in. It's on this slide. Well, that turned out to be very helpful, didn't it? Okay, that mistake out of the way. We've done and explained quite well, if you ask me, one of the conditions that a computer might test for. And another condition that I'm going to talk about is another type of comparator, a comparator condition. And we're going to compare two numbers again, but this time, instead of comparing if they're equal to one another, I'm going to compare if the first number is greater or the second number is greater. Or even if the first is smaller or the second is smaller, you can compare the same. They are the same thing after all. I'm not going to go over the circuit for this one because it's very big and there's a lot of wires involved, so it's quite complicated. So I'm not going to go over the circuit for that one. One more condition that the computer might decide is if the carry from an addition goes past the most significant bit. So I haven't explained what most significant and least significant means in terms of the bit layout or of a binary number. So the most significant bit is the bit all the way to the left. So if you have 4 bits, if you have 0, 0, 0, 0, the most significant bit would be the bit that represents the biggest number. So it would be the 16 all the way to the left. The least significant bit would be all the way to the right. It's always 1 unless you're using fractions. But I'm not going to get into that. I don't use fractions in most of my computers. Usually for you and usually for me, 1 is going to be the least significant bit and the most significant bit will be whatever's all the way to the left. But if you're doing an addition, like if a computer is doing a sum and it carries left, if you have a 1 plus 1 in one column, it will carry, of course, and it will put the other thing, the carry onto the next bit. If that goes past the number of bits that the computer can handle, you might want a program saying you've given us numbers that are too big to add, or something like that. So you have a condition. If the carry does go too far, you have a condition, and you will tell the user on your conditional branch that the numbers are too big and you can't do the addition sum reliably. So yeah, that's all of the conditions that I'm going to go over for this series. There are a few more, but I haven't taught you about multipliers, dividers, things like that, so I won't go over that. Okay, so what you should have got out of this was when will a computer branch, when is a conditional branch necessary? So the conditions basically that a computer will rely on. And in the next video, I want to explain some types of ROM, read-only memory, mainly PROM, so program ROM, because you can get quite a few types of that. I haven't actually planned that episode yet, but I'll be doing that shortly. And at the end of this series, hopefully you should know how to write some basic programs, and you should be able to not build, but you should write programs for very basic computers. I hope you enjoyed, I hope you learned. I'll see you next time.